So today we are going to see the last concept, quadratic forms in the eigenvalues and eigenvectors. So that is the last topic of the course also, right? So quadratic forms, in the name itself there is quadratic. Quadratic means of order 2, right? So it will be defined as, basically it would be defined as a homogeneous expression of second degree in any number of variables is called quadratic form. A homogeneous expression of the second degree in any number of variables. Any number of variables is called quadratic forms. Suppose if there is a set of n numbers or n variables, then the expression, then its homogeneous expression can be defined as follows, that the homogeneous the expression of n variables, how we can define? Can anybody say? There are n variables are there, x1, x2, x3, so on, xn. Then its homogeneous expression.
Sir, it can be like x1 square plus x2 square plus x3 square into ax4 square, something like that.
It is not whole square, right? So it is homogeneous expression of second degree. So every term it is of second degree only. It cannot be more than that or it cannot be less than that. So for n variables we have to be sum accordingly. So therefore it can be defined as the quadratic form of n variables, say x1, x2, so on, xn is an expression, that is homogeneous expression of the form sigma I is equal to 1 to n, sigma j is equal to 1 to n, aij into xi into xj, xi into xj. Xi into xj, right? This is can be extended in a way that will be, for I is equal to 1, we will run j1 to n, a11 x1 x2, x1 into x1, that means x1 square. Can we write x1 into x1 square plus a12 into x1 x2 plus a13 into x1 x3 plus so on plus a1n into x1 xn plus for I is equal to a21 x2 x1 plus a22 x2 square plus a23 x2 x3 plus so on plus a2n x2 xn plus so on plus an1 xn x1 plus an2 xn x2 plus so on plus ann xn square, right? This will give the expression. So of n variables, all of them are of homogeneous of degree 2. Every term which has degree 2. So this is the accommodation. So therefore, so in which let us assume if x is equal to the set of variables x1 comma x2 comma so on xn a vector, then this expression, can we expect how it can be expressed? X transpose A into X. This is Q. Usually it defines Q is equal to X transpose A into X. A into X. That is given by sigma I is equal to 1 to n, sigma j is equal to 1 to n, aij, xi, xj. So if you take it X transpose is equal to this one x1 x2 so on xn and multiply with some coefficient matrix A and X, it will give you the homogeneous terms. This form, this expression, it is called the quadratic form. Quadratic form. Let us see here. This this can be written as, it's clearly written as x transpose A into X. X transpose A into X. Also, this we may be written in a way that x11 a11 x1 square. Here you see x1 x2, here x2 x1. Their coefficients may be differ, but the term is of second order with the same x1 into x2. So therefore this we may be added. That means a12 plus a21 into x1 x2 plus similarly a13 plus a31 into x1 x3 plus so on. We can write it as plus ann xn square. Okay, x2 square also it will come, a22 into, here it will be a22 into x2 square plus so on, like that. All the terms will be written in such a way. So therefore this can be written as, if we written that the coefficient matrix A, where A will be like this, right? A11, A12 so on, A1n so on, an1 so on, ann. But the position of 1 2 position, there the coefficients may be different, that sum of some constant it will be, the constant it will be equally shared for 1 2 position, right? So this we can write it, put Cij is equal to 1 by 2 into Aij plus Aji. Aij plus Aji. So therefore, it result in U, that implies Cij is equal to Cji. So that the coefficient matrix in the quadratic form, you can say, what is the coefficient matrix in the quadratic form? What it is? what will be that? It is also can write the quadratic form Q is equal to X transpose AX is also can be written as Q is equal to in such a way Cij, where Cij is equal to, we can define like this, right? Where Cij is equal to Cji. So that means all the Ij positions were equally shared. So when Ij position is equally shared, that means it resulting in a symmetric matrix, right? So therefore, the coefficient matrix in the quadratic form is always symmetric. Is always symmetric. So now let's see here some of the examples. We can see for the quadratic forms 4x square plus 7xy minus 9y square is a quadratic form of it is not of in x and y, two variables, right? In two variables, quadratic form in two variables x and y, right? Number two, we can take it 2x square plus 3y square minus 4z square plus 2xy minus 3yz plus 5zx, right? It is also a quadratic form in three variables x, y, z. In three variables x, y, z. So can we write them into the expression sigma I into such a way? What will be the coefficient matrix of them? Where x is equal to xy, two variables only. So therefore the quadratic form can be written as x transpose A into x. So therefore this one we can write it 4x square x into x, that means that resulting you 1 position, plus 7 into xy, right? This xy position means it will be 1 2 position, 1 2 position to be equally shared with 7. So therefore 7 by 2 xy, right, plus 7 by 2 yx minus 9 into y square. So therefore this we can write it easily in the quadratic form, that is x y x transpose into, so the position 1 position constant for 1 2 position 7 by 2, that 2 1 position 7 by 2 and minus 9 into, we can write it xy. So it resulting you the required quadratic form. This is Q is equal to x transpose into A into x, where A is equal to the coefficient matrix. A is 4, 7 by 2, 7 by 2 minus 9, right? This is very clear, a symmetric matrix, right? This is a symmetric matrix. So if the coefficients in the quadratic form all are real, then it is called the real quadratic form. If the coefficients in the quadratic form are real, all the coefficients are real, then it is called the real quadratic form. Otherwise it may be complex. Okay, good. So therefore now we can we write here for this quadratic form, what is the coefficient matrix? A, can you find out? Can you find the coefficient matrix of this?
Yes, sir.
Can you find?
Yes,
Find. Tell me. So given Q is equal to 2x square plus 3y square minus 4z square plus 2xy minus 3yz plus 5zx. Okay, it is very clear. The quadratic form has three variables. So therefore, assume x is equal to x, y, z. Three variables, the vector. So therefore, the quadratic form will be x transpose A into x. So therefore, that Q can write it 2 into x square, 1 position, plus 1 2 position x1 x2 2 into xy where it is, xy it is coefficient is 2, that we have to be taken as accommodated equally in the two positions, 1 2 and 2 1 position. Okay, so therefore 1 by 2 into 2 xy plus 1 by 2 into 2 xy yx. Okay, 1 1 1 2 position plus 1 3 zx, 5 by 2 into xz plus 5 by 2 into zx, so it will give you 5zx plus next 3y square, y into y, x1 into x2 into x2 like, plus 2 3 position yz minus 3 by 2 yz minus 3 by 2 zy plus sorry not plus, minus again 4z square. So like that you can write it, and you can write in the matrix form, that is equal to x is, that is equal to x transpose a into x we have to write. So x transpose is x y z into coefficient matrix a11 2 a12 half a13 5 by 2, right? Next a21 1 by 2, a22 3, a23 minus 3 by 2, right? a13 5 by 2, 2 3 minus 3 by 2, and a33 minus 4, right, into x y z. So if you multiply this, it resulting you the above expression, that is in the homogeneous expression of order 2 of degree 2. Okay, this is the required a. Therefore a is equal to the coefficient matrix a is equal to 2 1 by 2 5 by 2 1 by 2 3 minus 3 by 2 5 by 2 minus 3 by 2 minus 4, right? So now let's write the quadratic expression if they given the matrix. Right, find next example, find the quadratic form of the coefficient matrix of the matrix. I am giving you here two. One is 1 2 5 2 0 3 5 3 4, and another one AHG HGF GFC. Can you find the quadratic form of these matrices?
Yes, sir.
Find out and tell me what is the expression for one. You see that this is of A is of order 3 by 3, and both of them. So therefore, how many number of variables it will be for getting the, for generating the quadratic form?
3.
X is equal to 3 variables. Say x1, x2, x3, or x, y, z, whatever it is you convenient. You can take it. So for first one, Q is equal to x transpose A into x. And directly to write it, x square. This you may be write it x1, x2, x3 position in the same way in column wise also x2, x3, x1 into x1, x1 into x2, x1, 1 3 position like, right? X1 square.
Sir, can you please solve this question using that matrix multiplication? Because sir, I'm little confused, sir. Between, sir, You have written Q is equal to XTAX, right, sir?
Where?
Sir, generally we write Q is equal to X transpose into A into X.
Yes, right.
So, sir, when I am multiplying using that first question you have written in third part, I cannot solve that question, sir. Can you please show that
Which
using
one?
matrix multiplication?
Second question or first question?
So the third question, part 1.
Third question, part 1.
The last question you have given us to solve.
This one, huh?
Yes, sir. Sir, solve it using matrix multiplication, please, sir.
You can take it x1, x2, x3. Huh?
Yes, sir. Then.
Okay. So there you maybe x is equal to, it is a vector. Yeah. The transpose you can take this one. Matrix multiplication, it will be not compatible, na?
Yes, sir.
So therefore you take it as vector x is equal to, not like this, you take it like this, right? x1, x2, x3.
Now
That is
perfect,
all
sir.
you can do. First you do this and later come. Not to this and that this. Right? You can get it at anywhere. First you do last two where that compatibility will be exist. Later these two. Okay?
Now it can be solved, sir, actually.
That is not makes you confusion here clearly.
Okay. Fine, sir.
That may be a row vector or column vector. It may be it is a vector, that's all. Okay?
Okay, sir. Perfect. Thank you.
It will give you x square. X1, x2 is 2. And x2, x1 is also 2. 2 plus 2, 4. x1, x2 plus 5 plus 5. 10. x1, x3. There is no x2 square. 0 x2 square plus 3 plus 3, 6. x2, x3 plus 4 x3 square. This is the quadratic form of the first question, right? So that's why I just given you very simple clue that every coefficient matrix elements are like this only. Cij is equal to 1 by 2 into Aij plus Aji. Right? 1, 2 position, you take it as equal sum of them both.
Okay, sir.
Giving you the symmetric matrix. Right?
Yes, sir.
Okay. The second one, what is the expression? Q is equal to ax square 2hxy plus gy square. If you take for x is equal to xyz, you can practice accordingly. So therefore, gy square plus here g or b, you maybe take it so that no confusion. There are many g's are there. Please see the correction here. In the second matrix, b you take. B you consider, right? By square plus two g xz plus 2f yz plus cz square. Right?
Yes, sir.
Now this is the quadratic form. So do you have any doubt in this? I can explain you because it is very important.
No doubt, sir.
How? So there are two aspects we have seen. One is from the quadratic expression we can find out the coefficient matrix. From the given coefficient matrix we can write the quadratic form, right? In both the ways we have seen the how work out these extract from quadratic forms from the matrix or matrix from the quadratic form. Now there is one more definition which we can say, that the rank of the quadratic form Suppose if Q is equal to X transpose A into X be a quadratic form in R, the set of real numbers. That means it is a real quadratic form. Okay, then the rank of the quadratic form is defined as rank of its coefficient matrix. Rank of its coefficient matrix. That means rank of Q is equal to rank of A. Rank of A, that is equal to rho A. We can define. If A is of rank R, then rank of the quadratic form is equal to R. Okay, this is one thing. And there is another thing important here, that is canonical form. Canonical form or normal form or sum of squares. Sum of squares form. Usually these quadratic expressions which have very lot of physical significances, in finding the nature of them, so it is more difficulty we can for getting the nature of the quadratic forms as it is in the homogeneous expression. But that nature can be easily obtained or defined by reducing this into the canonical form or sum of squares. If we write this into the sum of squares, we can easily to get at their nature of the canonical quadratic forms. So how we reducing these quadratic forms into the canonical forms are sum of squares, where given that the quadratic form is Q is equal to X transpose A into X. How this can be reducing into sum of squares? Can anybody think? Here, the given that quadratic form is X transpose A into X. X transpose A into X. How we can reduce this into the sum of squares? This is my
Sir, by making A as an identity matrix.
where A is the real symmetric matrix, where we know where A is real means if Q is the real quadratic form, then it may be real symmetric. Real symmetric. I already given you where in discussion of the similarity transformation before the diagonalization, right? If A is a symmetric matrix, it results in you the orthogonal model matrix, right? So therefore, what it result in you X transpose A into X. This is a homogeneous expression. There is no doubt at all. This resulting you a homogeneous expression that will give you of forms like this: ax square plus xy. Suppose if it is of 3 variables, it will be accordingly coming all the homogeneous terms of degree 2 in 3 variables. So now, suppose for this x is 3 variables, how we can write it this into ax square plus by square, or sorry, c1x square, c2y square plus c3 z square. That c1 c2 may be lambda 1 x square plus lambda 2. That variable also, it is not compulsory that should be x y z. There may be very different. I am just writing you differently. That will giving you in a way that say sum of squares. This will be lambda 1 say y1 square plus lambda 2 y2 square plus lambda 3 y3 square. So how we can obtain this total expression into sum of squares? The sum of squares form is this. This is said to be the canonical form of the quadratic expression, quadratic form. Okay? That quadratic form, any real quadratic form, Q is equal to X transpose A into X, which resulting you the homogeneous expression of degree 2 in the variables X. Now this reduction into sum of squares, that is normal form. Why? Because so that similarity to be extended. So for getting the similarity, so we will make the transformation, one simple transformation. By applying this transformation to this expression, it will be homogeneous quadratic form will go into the sum of squares. How that sum of squares will be
diagonal.
If A is diagonal matrix, right? If A is diagonal matrix, then obviously X transpose AX will give you
Sir, that square summation
Sum
form.
of square forms.
I think,
Sum
yeah,
of
you
square
got
form.
the point. That if this coefficient matrix is diagonalized, then we can get it the sum of squares form of the given quadratic form, right?
Yes, sir. Yes, sir.
Yeah.
Yes, sir.
Now that diagonalization will work out here. So we need to diagonalize the matrix A. If we diagonalize the matrix A, that will give you through some transformation that will result in you y transpose d into y. So this is sum of squares or normal form of the given quadratic form. See, here we can define the canonical form of a real quadratic form. Q is equal to X transpose AX is defined as Y transpose D into Y. Y transpose D into Y, where D means diagonal value, diagonal matrix, where diagonal matrix, their diagonal elements only, it's eigenvalues. So therefore there we can write it, or lambda 1 y1 square plus lambda 2 y2 square plus so on plus lambda n yn square, which can be obtained through the orthogonal transformation, right? Which can be obtained through or by an orthogonal transformation. How we can get it, that orthogonal transformation? What will be its orthogonal transformation? If P is the model matrix is orthogonal, then it results in you the transformation x is equal to Py. Suppose if Q is equal to, here I am just writing you, if Q is equal to the given one x transpose A into x, where n variables. So therefore A will be of order n, where x is equal to x1, x2, so on, xn transpose n variables, and A is of order n by n, right? So how this orthogonal transformation, because that is equal to symmetric matrix, right? So therefore there find out the eigenvalues and eigenvectors. There will be orthogonal, so therefore that result in you the orthogonal model matrix, which is P, right? So from that expression, if you put it, the transformation x is equal to Py in the above, you see what will be happen? Q is equal to x transpose Py whole transpose A into P into Y, that is equal to Y transpose P transpose A into P into Y, right? That we can group it P transpose AP. If P is orthogonal model matrix, then what is P transpose AP? P transpose AP is equal to D, right? It results in you Y transpose D into Y, right? This is the canonical form. This is the canonical form of Q, quadratic form, right? Any doubt in this? This canonical form can be obtained by the orthogonal transformation x is equal to Py. So from the coefficient matrix A, you obtain that orthogonal matrix P. So hence P inverse P transpose AP resulting U D. So therefore that Py become Y transpose D into Y, resulting you the required sum of squares. Sum of squares, where P is the model matrix and D is the diagonal matrix, right?
Yes, sir.
Right. So now we can define some another definitions where we can here. I hope you have been understood that what is the quadratic form and what is its canonical form, right? Canonical form is sum of squares form. There is no loss of any nature of the quadratic form. It just expressed into the canonical form through the orthogonal transformation. X is equal to orthogonal model matrix, given matrix into given quadratic form into sum of squares. Sum of squares, right? That resulting you the form that is lambda 1 y1 square plus lambda 2 y2 square plus so on lambda n yn square. So here we can see the some of the definitions that are index. Index. It is denoted by S. It is denoted by S. Index of a quadratic form is the number of positive terms, number of positive square terms. We can write it. Positive square terms in its canonical form. Okay, S is the total number of positive square terms. Okay, it's denoted by S. S of a quadratic form. S is equal to total number of positive square terms in the canonical form. That is also defined the number of positive. How we can relate with the eigenvalues? That how canonical form it will be lambda 1 y1 square plus lambda 2 y2 square plus so on plus lambda n yn square. So therefore, how we can say that they are the positive values, and with the index in terms of the eigenvalues, coefficient matrix, right? Right? Yes, index. Next,
Yes, sir.
signature. Signature. Signature is defined is the difference of positive and negative square terms. Square terms in the canonical form. Canonical form. Here we have defined that rank of the matrix, rank of the quadratic form, that is rank of the matrix. Suppose a matrix is of order n by n. N by n. If rank say is equal to R, coefficient matrix rank is say R, then rank of the quadratic form is equal to R. Then how many number of eigenvalues are there will for A? How we can relate that rank with the eigenvalues?
N minus R.
Rank and eigenvalues, number of eigenvalues. If rank 3, how many eigenvalues will be there? If rank 2, how many eigenvalues will be there?
Sir, R.
Very good. So now suppose if the rank of the given matrix is n, then n eigenvalues are there, right?
Correct.
So therefore, how we can relate that the rank with the quadratic rank, the rank with the eigenvalues?
Rank is equal to number of eigenvalues.
Right. Number of eigenvalues, in which positive and negative, that positive number of eigenvalues are said to be the signature, are said to be the index, So then signature can be defined. Suppose S is the signature, that is number of positive terms minus, and how many number of negative terms are there in its canonical form? Suppose there are the rank of the matrix is R, say rank of A is equal to R, that is equal to number of eigenvalues. So then, in which S are the number of positive eigenvalues, then how many number of negative eigenvalues are there?
R minus S.
Very good. So therefore, this is signature. So hence, we can define that signature is 2S minus R. Right? Understand?
Correct. Yes, sir.
The difference of positive and negative square terms in the canonical form is 2S minus R, where S is the signature, the total number of positive eigenvalues, and R is the rank.
Sir, S is not signature, it's index.
So therefore, S is the index and R is the rank. The signature can be defined 2S minus R. Right?
Right, sir.
Right. Signature is equal to difference of positive and negative square terms, that resulting you 2S minus R. Right. Next, nature of the quadratic form. Nature of quadratic form. Suppose let the quadratic form let Q is equal to X transpose A into X, A into X, be a quadratic form in n variables. N variables. Okay, is said to be. Here write it okay, full stop, and the quadratic form is said to be. I will write it point by point. Then the quadratic form is said to be number 1, positive definite. This is definition. The nature will be defined into positive definite, negative definite, okay, positive semi-definite, negative semi-definite, indefinite. Like that we can classify the nature of the quadratic forms. So the positive definite, a quadratic form is said to be positive definite if R is equal to N and S is equal to N. How can we understand this? If R is equal to N and S is equal to N, what it means?
Sir, all the square ones are positive ones.
Yes.
Right. In the canonical form of the quadratic form, all the terms are positive. S is equal to N. Suppose it is of N variable quadratic form, so therefore its canonical form will have N square terms, right? N
Yes,
square terms. N square terms. So where S is equal to N indicates its index is equal to N. Index is equal to N. Don't confuse with S. S is not a signature. S is an index. There is no letter for denoting signature. So where S is indicating the index. Index means number of positive square terms. So if only n number of terms are there in the quadratic form where with n variables, so therefore all of them must be positive. If all the square terms are positive, that rank of A is equal to R, that is equal to N. Rank of A must be N. Therefore, det A not equal to 0, right? Rank must be is equal to n. That is determinant not equal to 0. So therefore, and all the square terms will be positive. Okay, that this also in terms of eigenvalues we can define, that is if all the eigenvalues of A
Are positive.
are positive. Okay, good. So if a quadratic form is like that, then it is said to be positive definite. Number 2, negative definite. If R is equal to n and S is equal to 0. So determinant not equal to 0 and rank of A is equal to n and index is equal to 0. There is no positive terms. That means all of them are negative eigenvalues, right? Or if all the eigenvalues of A are negative, then it is said to be negative definite. Next, positive semi-definite. Positive semi-definite. If R is less than n and S is equal to R. Okay, understand what it
Yes, sir.
indicates?
Yes, sir.
What it indicates? Explore this.
It indicates all are positive, but rank is less than n.
Rank less than n means determinant is equal to 0.
Yes,
Right?
yes.
Det of A is equal to 0. Det of A is equal to 0, where rank of this matrix is less than n. So that means if det is equal to 0 means there at least one eigenvalue must be
Sir, 0.
0.
0, exactly. So because if determinant is equal to 0 with n by n of order matrix, then obviously that eigenvalues will be less than n. So therefore one eigenvalue must be 0, right? Yeah. So and one eigenvalue must be 0 and the remaining all eigenvalues will be positive. So then that quadratic form is said to be positive semi-definite. Positive semi-definite. So this is what we can write it. If all the eigenvalues of A are greater than or equal to 0 and at least one eigenvalue is 0, right? This is positive definite, positive semi-definite. Next, negative semi-definite. How we can define? If R is less than n and S is equal to 0, right? Or if all the eigenvalues of A are less than or equal to 0 and at least one eigenvalue is 0. One eigenvalue at least is 0. Okay. Next, last one, indefinite. A quadratic form is said to be indefinite if in all other cases, all other cases, or if A has positive as well as negative eigenvalues. Okay. Here one more note point we can. If Q is negative definite, then minus Q, the quadratic form, if the given quadratic form Q is negative definite, then minus Q is
It's a positive definite.
vice versa. Okay, semi-positive, or maybe here also negative definite or semi-negative definite. This will be semi-positive definite. Like this also we can define. Suppose if Q is semi-negative definite, then minus Q is semi-positive definite. If Q is negative definite, then minus Q is positive definite. Okay, understand? Like this we can define the nature of the quadratic forms. That nature can be decided based on the eigenvalues or based on the canonical forms. Okay. We will do the problem for reducing the given quadratic form into canonical form in the next class. That will be the last class we can see it. Okay, any doubt in this?
No, sir.
Okay.
Sir, tomorrow quiz timing?
Not tomorrow, day after tomorrow, not quiz.
Yes, sir. Yes, sir. Saturday quiz timing. What is the quiz timing, sir?
We will convey you. I think your examinations will start from 27th and there will be Viva. Okay. I think
Okay, sir.
might not be
Okay, sir.
written exam. They will be through Viva only, they will be conducting the exam. Okay, get it prepared well.
So when will date sheet come, sir? The schedule of the exams?
Very soon. They have been released the tentative schedule also, 27th onward.
Okay, sir.
7th September, by end of this month. Okay.
Okay. Thank you, sir.
Just a minute. Wait. I will have to download your account. Good. Okay, students.
Thank you, sir.